Today I'm going to discuss about the material strengthening mechanisms. So normally when dislocations are there, the strength of the material it is going to be decreased. To improve the strength of the material, we have to use certain mechanisms. So today that mechanisms I am going to explain you. So these are the topics that I am going to cover today. First, I am going to give the basic definition of what is strengthening, and next, what are the different types of mechanisms we have. So these are the four different types of mechanisms we are using for improving the strength of the material. The first one is the grain size reduction. The second one is the solid solution alloying. Third one is cold working, that we can call it as strain hardening, and the last one is the annealing. Normally the annealing it is consisting of three different steps, that is recovery, recrystallization and the grain growth. So first we'll see what is the strengthening. The strengthening is nothing but the ability of metal to deform plastically. It will depends upon the ability of dislocation to move. Normally when material it is going to be deformed plastically, the strength of the material it is going to be vary. So when there is a more dislocations in the material, that means when the atoms it is going to move from one place to another place, the dislocations it is going to happen, right? So at that time the strength of the material it is going to be decreased. So when we prevent that kind of things, we can improve the strength of the material. The hardness and strength are both are related. How easily a metal plastically deforms by reducing the dislocation moment. The mechanical strength also it is improved. So here when we will prevent the dislocations in the material, the hardness and strength, these two are interrelated, right? So when we are going to reduce the dislocation moments in the material, the strength of the material it is going to be improved. To the contrary, if dislocation movement is easy, that is unhindered, the metal will be soft and easy to deform. So when there is a dislocation movement is very easy, so at that time the metal it is going to become very soft and also it is very easy to deform. So these are the different strengthening mechanisms we are using. Okay, grain size reduction, solid solution alloying, strain hardening, annealing. So first we'll see what is grain size reduction. See here in the diagram, so they mention very clearly. So these are the grains. So these are the different grains are there in the lattice space. Okay. So the grain A, the grain B. So these are having the very small size grains. Okay. So when there is a smaller grain size, there is a more barriers to slip. That means the slipping is prevented when there is a more boundaries. Okay, and also the grain size also it will depends. If the smaller grain size, the more barriers to slip, the barrier strength it is going to be increased with misorientation. So normally when there is a grain boundaries, so this grain boundaries it is work as a barriers to the slip. That means the movement of the atoms it is not going to happen when there is a grain boundaries. Okay, so that it work as a barrier for the strength and it will increase the strength of the material. So there is no movement of the atoms will be there if there is a any grain boundaries. The grain boundaries it will prevent the movement of the atoms from one place to another place, so that so we can increase the strength of the material. So normally when there is a smaller grain size, okay, there is a less movement of the atoms will be there, so that there is a less movement of the atoms, that means there is a less dislocations, the strength of the material automatically it will be increased. So this is the formula to calculate the yield strength. Okay, so the yield strength in this equation, so we are going to calculate by using this formula. In this equation, it indicates that the yield strength has an inverse square root relation with the grain size. Okay, so if you see here, so this D, the D indicates the grain size. The yield strength it has an inverse square root relation with this grain size. Okay, theoretically a material it can be made infinitely strong when the grain size it is made up of very infinitely small. That means when there is a small grain size uh, is there in the material, so automatically it is having the great strength. The strength of the material it is always more. This is the second one, solid solution. The impurity atoms normally it will disturb the lattice and also it will generate the stress. Okay, the stress it can produce the barrier to dislocation motion. So here you see, so these are the impurities, the small impurity and the larger impurity we are considering. So when there is a impurity atom in the lattice, that will distort the lattice and also it will generate the some stress. That stress it can produce a barrier for the slip. So that stress it will help us to increase the strength of the material, because the stress it will act against the dislocation. So here if you see this diagram, so here there is a small substitutional impurity is there. So because of this small impurity in the lattice, so here the local shear it is going to be produced or generated. See A and B here in the two different locations. So when the impurity atom it is occupying in the lattice space, so it will generate the shear at A and B. So this shear stress it will opposes the dislocation motion to the right. So here this is the direction. So in this direction that movement it will be prevented because of this two shear stresses developed because of this impurity atom. So here we are considering the largest substitutional impurity. So because of the impurity, the local shear at C and D it will be generated and also it will opposes the dislocation motion to the right. So when there is a dislocation motion is less, that means when there is a no dislocation of the atoms, automatically the strength of the material it is going to be improved. So when there is a barrier like to move the atoms from one place to another place, that means there is, if no slip, the strength of the material automatically it will be increased. What is cold working process? This cold working process also we can call it as strain hardening. What is strain hardening or cold working process? See here. So these are the different cold working processes. Normally we are going to deform the structure of the material at the room temperature. This is the common forming techniques which we are using to change the cross sectional area. So these are the four different types of forming techniques, that is forging, rolling, drawing and extrusion processes. In this all processes what we are doing, just we are changing the cross sectional area. In cold working process we are not going to use any heat to change the microstructure of the material, only we are going to change the cross sectional area without changing any structure, so that we can improve the strength of the material, especially when you are going to change the cross sectional area in the component or the material, the mechanical properties it is going to be vary. So here if you see the structure, the dislocation how it is going to happen during the cold working process. Normally in the cold working process the dislocations it will be entangled one over the other during the cold working process, and dislocation motion it will become more difficult, which makes the material very stronger orally. So this is the result of cold working. If you see this diagram, you will understand the yield strength it is going to be increasing because of the cold working process, because here the dislocation density it is going to be increased, which leads to increase in the yield strength. Okay, so that the material it becomes very harder. And also here when you are doing this cold working process, the ductility and tensile strength of the material also it is going to be increased. In this diagram you see the blue color light, it is showing the small hardening. The red color it is showing the hardening, large hardening. So when we are doing the large hardening, the strength of the material normally it is more when compared to the small hardening. The yield strength also it is going to be improved when we are doing this kind of large hardening when compared to the small hardening. So when you do this cold working process, normally the hardness and also the ductility and tensile strength of the material it is improved. So this is the formula to calculate the percentage of cold working. So here we are considering the two different cross-sectional areas. Before doing the cold working process, what is the area, and after cold working process, what is that area? Both we are going to consider, and by doing this, we are going to get it the percentage of the cold working process. Here in the diagram we are showing, this is the diagram before the cold working process. The diameter is 15.2 mm, right? So after doing the cold working process, that is strain hardening, the cross section area it is going to be changed, because here the diameter is going to change, right? When there is a change in the diameter, obviously the cross sectional area it is going to be changed. Initially it was 15.2 mm, but after cold working process it is decreased to 12.2 mm. So by taking these two values consideration, so we are going to calculate the percentage of cold working. Okay, so normally if you consider these two values, we are going to get 35.6% of cold working. So this diagram will shows the cold rolling illustration. Okay, before rolling and after rolling how it is. Okay, so normally before rolling it is look like a isentropic, but after rolling so it is a anisentropic direction. Normally before rolling the grains are approximately it is in spherical shape, and also it is equiaxed and randomly it will be oriented, but after rolling the grains are arranged in the proper manner, and also the rolling it will affects the grain orientation and shape also. Okay, so it will be arranged in the proper manner, and also the grain size also it is going to be changed. So this is the last one, annealing process. Normally in the annealing process, the material is going to be heated to the above crystallization process, and again we are going to cool down it. Okay, initially we are going to heat the material to the high temperatures, normally above the critical temperature. Above the critical temperature, we are going to heat the material. So there it is going to change its microstructure, and then again we are going to cool down to the normal temperature, so that so we are going to change the some mechanical properties of the material. Okay, and also here we are talking about the strength of the material, right? The strength, mechanical strength, it is going to be increased by doing this annealing process. Normally the main purpose is to improve the cold work properties by increasing the ductility and retaining the most of the hardness. I told you that in annealing there is a three different steps are involved, right? So that is a recovery, recrystallization, and grain growth. So here in the recovery, normally when you are going to supply the heat above the recrystallization temperature, the atoms, the plane of atoms, it is going to relieve its internal strain. The strain energy it is going to be relieved, so that the this through dislocation motion due to the enhanced atomic diffusion at the elevated temperature, the atoms are arranged in the proper manner, that leads to the reduction in the number of dislocations. So if you see this diagram, you will understand. Initially, the atoms are arranged in the randomly. Okay, so but after recovery process, the atoms are arranged in the proper manner. It is systematically, it is arranged in the plane. The next one is a recrystallization. After recovery is completed, the grains are still in a relatively high strain energy state. Okay, even though after recovery process, still it is having some sort of the strain energy within it. So that it is going to be relieved in the recrystallization process, so that we are going to form a new set of strain free and uniaxial grains, so that are having the low dislocation densities. Okay, the driving force to produce this new strain structure is the internal energy differences between the strained and unstrained materials. The new grains it forms a very small nuclei, and they grow until they consume the parent material. So here in the recrystallization process, it is going to be form a new set of strain free, completely strain free and uniaxial grains that are having very low dislocation densities. Normally the driving force to produce this kind of the strain free and uniaxial grains we are going to get because of the internal energy differences between the strained and unstrained materials. Okay, the new grains, whatever we are forming because of this process, so it is having the very small nuclei, and also it will grow continuously until it will consume the parent material. So here this is the recrystallization process illustration, how it will be. See, the first one, it will indicate the cold working grains. Normally before doing the annealing process, it will be like this. Okay, after initiating the recrystallization process, after the 3 seconds at the temperature of 580 degrees centigrade, so here the recrystallization initially it will be like this. So after partial replacement of the grains after 4 seconds, so it look like this. And then completely recrystallization process, so after the 8 seconds it is going to happen, so that will be like this. Okay, the last step in the annealing is the grain growth. Normally after recrystallization, the strain free grains will continue to grow if the metal specimen is left at the elevated temperature. So normally after recrystallization process, the grains continuously it will grow. Suppose if you are keeping the metal or the component, that specimen still it is in the elevated temperature, so the strain free grains it will continuously it will grow. Okay, the strain energy whatever we are getting through the recrystallization process, it is completely, it is strain free, right? So that it will be uh, help to continuous growth in the grain size. Suppose if you are keeping that metal or the specimen in the elevated temperatures, suppose if the grains it will increase in the size, the total boundaries are decreases, the boundary area it is going to be decreases. Suppose if the grain size continuously it is going to increase, the boundary area it is going to be decreased, so that the total energy also it is going to be decreased. Okay, if there is a large grains growth at the expense of smaller grains, so these are the different mechanisms that we are using to improve the strength of the material. Thank you.